So this is our stellar evolution, and years ago I think this was the slide that set off my little creationist students, and when I got to the part about how the Earth is formed, one of them raised his hand and said, if I don't believe the Earth was made that way, do I have to still learn this stuff? And my answer to him was, I usually can't think on my feet. But I had a pretty good answer, and the answer was, IB thinks the Earth was formed that way. And your parents have paid for you to take the IB test, so you should probably learn that version of existence. Yeah, there we go. You know, of reality, or you know. But anyway, basically, astronomers have an advantage over biological. Evolution just means to change over time. Okay, it doesn't mean the devil. And although, you know, I could see where the confusion might be there. And astronomers actually have a advantage over biologists, right? And that is that this evolution is actually fairly simple, and we can go back in time. We can just look farther from the Earth. If we look 1 billion light years from the Earth, we can see the galaxy or the universe as it was 1 billion years ago, right? And if we look 5 billion light years from the Earth, we're seeing light that's getting to us from 5 billion years ago, right? So big telescopes are like time machines, right? And then as far as tiny things, as far as particles go, the Big Bang was this incredibly energetic event. And that's what the Large Hadron Collider is for. It's a time machine as well. We're going back in time. We're getting higher and higher energies and looking at what the laws of physics were at those energies, which is back in time, right? Now it's pretty non-energetic. Every photon from the Big Bang is the temperature is about 2.7 kelvins, right? So it's microwave. Basically, it's just like microwaves. But it started out having so much energy. The photons had so much energy that they could create willy-nilly protons from pure energy, right? And you know, anyway, so this is a crazy thing. This is an overview of the life of a star. I gave you guys this flow chart of stellar evolution, okay? And your assignment is, after we're done with this, we'll be done with this after tomorrow probably. We won't get to everything today because we need to spend quality time on this. But what I want you to do is go to that website, and they've got, if you go to that website, okay, they've got a interactive flow chart. Okay, question 3, let's go. There we go, previous. Question 2, previous. Stellar evolution, previous. Okay. There we go, start. There's your thing right there. And all of these questions, it's like a little, like in biology, you know, does it have 3 leaves or 2 leaves, right? You know, it's got a little binomial key or something like that. Is the mass of the protostar greater than 0.1? And when it says M, that means mass of the sun, right? No, what happens to this object? 2, where on the HR diagram is it? What is its energy source? So all these answers are there, right? So click on no. The answer to no is that you end up with a Jupiter-like planet. It's not big enough to be a star, but it's like a big ball of gas like Jupiter, right? Okay, blah, blah, blah. Become a planet, which can be quite warm initially. Spend the rest of its lifetime cooling down, right? And then you can go back, or you can click the thing, right? And then if a yes, it's bigger than that, then they talk about, they've got pictures. Isn't that neat? That's kind of neat, isn't it? Kind of like an interactive tool there. And the reason I'm giving you this is that I'm just sort of going to give you kind of bare bones stuff that mostly comes out of your textbook. We're going to talk about some processes, but this has got the nitty gritty of, because kids are always wondering, well, what if the star is this size, or what if the star is this size? You know, what happens to it? Yeah?
I just looked it up. Apparently we could fit about 1.3 million Earths inside the sun.
1.3 million by volume, yeah. Yeah. That's a lot, right? Like, you know, if I start to fill the little Earth sphere with this big sun sphere, you know, 1.3 million, okay. Okay, let's go back to, merci. Okay, so we're going to form a protostar, right? This is the cloud of gas and stuff that's going to collapse, right? Once it collapses, apparently if it's bigger than 1/10 the mass of the sun, then it becomes a main sequence star. Main sequence stars, by the way, are ones that are doing hydrogen fusion, right? And turning hydrogen into something else. And then it could become a red giant, and how it becomes a red giant, why it puffs up so big. We'll talk about why that is, right? And then it could be a white dwarf, or it could supernova. And if it's supernovas, if it's big enough, right, it could become a neutron star, or be a black hole, right? If it's big enough, right? So super giant things are going to become black holes. Some of them are going to drop off at different places. Our star, our sun, I believe, is never going to supernova. It's going to become a white dwarf and just sort of, yeah? Okay. And then just a little bit of trivia. Do you know that the word dwarves isn't real? Dwarves with a V. It's dwarfs. I did not know that. It's dwarfs. Dwarves is from Tolkien. Apparently Tolkien made that word up. I think it should be a word. If Pluto's not a planet, then dwarves is a word. I'll make that compromise.
No.
All right. Okay, so this is a weird thing. Why do we have the hourglass? I don't know, right? Okay, but basically a protostar is that if you have a cloud of gas, every particle in that gas is attracted to every other particle. There's something called self-gravity. Yes? Don't we know this? Do we know this? Right? And so ultimately, a cloud, if it's disturbed, if there's a knot of material or something like that, right, then it's going to collapse in on that knot. And we can see this happening. There's lots of places in our own galaxy where we can see this quite close, and stars are being born. And when it collapses, basically all of that gravitational potential energy turns to heat. And that's what you need for fusion, is you need heat and pressure, okay? Because hydrogen nuclei repel other hydrogen nuclei. They don't like each other, and to get them to come close enough to each other, you need pressure, and you need to have them moving fast, so they go boom, yeah, yeah, pressure, and temperature, boom, yeah, okay. Then we've got the let's see if this thing, oh wait, let's see if this works. I don't think it works, but we'll try it, okay. Cannot open the specified file. Yes, I know you can't open it, but is it possible you could consult the registry and there might be a file program registered to that? You stupid
Probably not.
piece of crap software. Okay. Did I say it? Was that out loud? Okay. No. There we go. So here is a very, very disentropic nebula. Yes? I just made a whole bunch of particles here, and I didn't make too many because interactive physics doesn't like to have 5 bajillion particles, but it can handle these. And what I did with this was I actually gave these little flying wedges velocity, so this thing has a little bit of spin anti-clockwise. Watch what happens as it collapses. This is fun.
Lag. Galaxy. Yep. Interactive physics is
Okay, so let's reset it. What's as it runs? What's happening to the rotational rate as it collapses? Yeah, it's going faster and faster. So it's like those gates at IBII, right, where you pull yourself in, and by God, you know, if you're just spinning at all and you pull yourself in, you can't get to the center, right? And so you can theoretically show that almost any nebula has enough spin that it can't get small enough to start nuclear fusion. And this was a problem for a long time. Yes? I know. So let's stop, reset. Let's make these guys all 0. Let's run it. I love this. It's like, it's the incredible shrinking cube. No. Now it's gonna, oh my God. No. There's free cheese in the middle. Let's see that again. Kaboom! I should have something go boom.
You should just have the screen go white.
Yeah. Let's make it 1. I think this needs to be -1, right? -1. This is like way faster than it was. Let's see what it does now. It's like, dance with your partner round and round. Dance with your partner. Whee!
Oh, no, look at that.
Spinning too fast.